Hala Al-Sabagh, and I'm a practitioner and an educator in the field of environmental design. I'm an architect as well. So the main exploration is about the built environments, and the first slide shows different images from I think many cities worldwide, not only in Egypt, but they focus on new cities and new urban areas, new developments that are more towards greening and more towards approaches to sustainable urbanism, and the interventions within existing urban fabrics, as we see a picture from Alexandria. So we always face the challenge of intervening into existing urban environments. Under the topic or the issue of climate change in Egypt, Egypt is one of the vulnerable cities, as the case of many other one of the vulnerable countries in Africa, as the case of many other countries worldwide, and is expected to suffer from a heat rise of 4 degrees Celsius in Cairo alone by 2060, and 3.1 to 4.7 degrees Celsius across the rest of the country. So the heat rise and the consequences of the climate change and how it's affecting the country has been the main reason for the today's paper towards trying to cope with the records that we are obliged to according to the IPCC, trying to keep the emissions and the heat rise levels, the consequences of climate change within a certain limitation. The annual precipitation is also expected to change from 10 to 40 degrees Celsius by 2100, and a sea level rise of 0.5 degrees Celsius. A massive urban development has been taking place across different urban areas and rural areas across the country that integrates a lot of sustainable development goals. Massive urban structures focus on bridges and roads, designing future cities and trying to envision that, as the case of many other researchers across today's conference and other conferences as well. We try to focus on how do we bridge the issue of climate change and the changes that are taking place into the existing designs that we are producing as architects and urban planners, and into the existing fabric as well.
Sorry for interruption. I cannot see that you go through the other slide. It seems it's freeze. Could you please check that you share the presentation correctly? Because for me, it shows only the first slide. I don't know if other presenters and...
I've flipped, yes. So it's not taking place?
Yeah, it's not taking place.
Okay.
Now I can see that something changed.
Does it work now?
Yeah, it works. At least I can see the third slide.
Okay.
Thank you.
There are 6 major urban algorithms that has taken place over the countries across different urban and rural areas. One of the major social problems that has been taking place over the past years is the internal immigration from rural areas to urban areas as foreseen. Part of it is due to the envisioned quality of life that is offered and many other parameters. That problem actually of climate change affecting the rural and the urban areas as well, mainly in the context of Egypt, focuses on a low water supply and demand, because we are facing some water scarcity and water threats over time, food insufficiency due to the heat rise effect, and as well as the water scarcity. That is affecting agricultural land and green spaces across different cities, and health risks due to the heat rise and due to the air quality, whether outdoor or indoor as well. In that context, this paper is trying to or has analyzed different cities across the different climatic zones. So Egypt lies within the hot arid region, but within the country, we have different 8 climatic zones that has been classified previously. each of the cities within zone has a different climatic conditions that requires different interventions from natural cooling, artificial cooling, the use of materiality, and all the beautiful and different topics that have been discussed during today's conference and yesterday as well. We're trying to intervene and trying to summarize which actual parameters would be used in each and every city to be able to cope with the urban expansion that is taking place. The main focus of today's paper is to analyze 8 of the cities. Each city lies within a different climatic zones, trying to categorize those cities that face climate change, that have been affected most with the heat rise. So they face the highest differences in air temperature, humidity levels, globe temperature, and wind variations as well. And cities for extreme design conditions, because cities that lie within the south area have a much higher climatic conditions and heat risks compared to other cities, other coastal cities that are facing the Mediterranean Sea. The main aim is to try to categorize those cities for intervening with environmental design parameters. The paper uses the methodology of analytical method, trying to bring historical data from 2000 to 2017, classified into two areas or two periods between 2000 and 2008, 2009 and 2017, before the pandemic has struck, and uses also future weather data for 2 of the major cities and try to predict the future scenarios of heat rises for 4 different years: 2035, 2065, and 2090. Both data sets have been used to analyze the heat risks according first of all, to provide a climatic overview for each city, and then try to predict thermal comfort levels using the Raman tool. And of course, focuses on the aspect of thermal comfort, try to predict at the end the heat stress level, trying to categorize or have categorized each city accordingly. Uh, the focus of this paper uses thermal comfort, or the thermal comfort index, MPET, using Raman. MPET is the modified PET. The modified PET, which is the MPET, it takes into consideration or is more sensible to changes of clothing and wind variations. So this is just an example of one of the cities trying to predict the two climatic periods between 2000 to 2008, and then between 2009 2017, and try to categorize the changes of the climate.
Sorry for another interruption. I don't know, is there the host, is it possible for host to change the presentation, because it's stuck again, it's freezing, it seems it's freezing. I don't know, because I cannot change anything.
Now it's
So
working.
yeah, it's working now, but I don't know why after you present the slides freeze. Um, Please start again. I hope this time it works. Thank you.
So again, through the methodology, the method looks into summarizing historical data sets and future data sets using 2 different methodologies, trying to use those data sets into analysis of the climatic overview of those cities, and then using the climatic overview through the lens of thermal comfort. So the main focus of this paper is to try to analyze the climate and climate changes through the thermal comfort aspect. So it kind of bridges the idea of using thermal comfort as an index inside urban environments, microclimatic conditions, inside buildings, outdoor environments, to the more global part of analyzing the weather data sets. And that is done for the future scenarios as the sample shown at the bottom part, using the weather tool weather shift, and the upper part using conventional data analysis using advanced Excel sheets. The idea of using thermal comfort, the whole idea of using the index thermal comfort to analyze the weather conditions is the changes in metabolic rate and the changes in clothing. So the paper analyzes each and every city with changes of clothing. So only with the adaptation, the normal adaptation of people changing clothing rates between cooler month and warmer month, this has been conducted for the 8 cities, looking into the variations again between the data sets. The findings for each and every city has been compared with the conventional way, of course, of using the psychometric chart through any of the tools and for those specific climatic regions. The findings of the thermosensation boats and the thermal comfort trying to predict the heat stress has been used through the ASHRAE scale as well for each and every city. The findings of each city have been compared to the summary of findings for the publications provided for each context again. Looking into the different cities, the 8 cities, we can see different wide variations of more than 6 degrees Celsius according to the average MPET, or the average thermal comfort or thermosensation index. And according to that, each and every city, data set one is between 2000 to 2009. And then this is the next. It's not moving again?
The problem is that I guess you only shared the slide, not the screen. And less than 2 minutes remain. Yeah, I don't know when you stop, it works. But if you, I don't know how we can manage it, but you only see one slide and it's freeze. Yeah, you have less than 2 minutes. You can keep going because I guess we don't have time
so
to
it looks into
proceed.
It looks into the analysis of the
Yeah.
8 cities, categorizing them again with cities of most change. And these are the thermal comfort indices that have been analyzed. The red zone is the areas where caused high heat risks, and the darker red areas are the months with high, again, thermal stress. I'll try to move through that. The summary of the findings is categorizing the city of Cairo and Alexandria as the main two major cities. And you can see the thermal comfort index and the level of heat stress that is caused, trying to categorize them or categorizing them into climatic periods. So we get an area where there is a hot zone and then an area with a high heat stress. The reason for that is not providing comfort, but it is for categorizing the level of heat risk and heat stress levels for each and every city. Cairo and Alexandria were the most cities with milder conditions. Is the slides moving now?
No, it doesn't move. What I guess their presentation time is finished. If you
I don't
kindly,
get a few more time for that.
yeah, only 1 minute because
I will try to
you
wrap
have to manage. Yeah, you have to try to manage because next
why.
presentation will start exactly at after you.
Okay. I will jump into the future scenario for the city of Alexandria, showing the predicted heat stress level that is expected to rise in July and August. And you can see the present scenario and the future scenario. It's reaching more than 45 degrees Celsius in June, and that is by 2090. And by 2035, you can see an increase of more than 2.4 degrees Celsius. The city of Cairo is less vulnerable compared to Alexandria, though Alexandria has had a milder, a pleasant conditions. And then the other three cities have been categorized together: Siwa, Ismailia, and Al-Minya. And moving to the different categorized climatic zones according to the heat risk and heat stress levels.
Sorry for interruption. We have to finish the presentation because after you, another presenter, uh, we already asked the presenter to manage their presentation time to be at a maximum 15 minutes. Now I guess it's finished if I'm not mistaken. Yeah, it's finished.
Okay.
If you agree, we can stop the presentation, and also the audience, please make attention that you can send your questions using chat box. Dr. Elena and I try to manage to gather them. And at the end of the full presentation, you have 15 minutes time to ask a question from the presenters. So all the presenters will stay at the conference virtual room, and you can ask your questions directly. So if all persons agree, thank you for the presentation. We can go through the second presentation. Polly, if you hear me, you can share your, try to make sure that you share the whole your screen, not only one slide.
Okay.
Because unfortunately, I don't have any access to manage this issue.
Yeah.
Okay.
Just let that. So just to check, you can see that moving.
Yeah, it's moving. Thank you.
Perfect.
Thank you, Polly. Thank you, Polly. You can start.
Thank you. So my name is Polly Aylwin, and I am a final year PhD student from Loughborough University. And today I'm going to present to you our work on the application of infrared thermography for comfort research.
Yeah.
Thermal comfort is dependent on numerous factors, and by understanding the integration of these factors into a single state, we can use this to inform the design of, for example, indoor or automotive environments with air conditioning or heating systems. Specifically, skin temperature plays a crucial role in a person's perception of their thermal comfort. And whilst the exact relationship between the two is complex, by evaluating skin temperature distributions, we can use this as a valuable indicator. Skin temperature is currently often measured with thermistors or thermocouples. However, these do suffer some limitations depending on our application. For example, you can have an interference caused by the contact sensor itself or the attachment method, altering local heat transfer. Some are wired, which inhibits their use during movements. Others, we can't access the data in real time. And importantly, with all of them, they only cover a very small body surface area. So an alternative method is to use infrared thermography, which is beneficial particularly in this area of research as it's non-contact, non-invasive and portable, providing a more feasible field-based measurement. Automatic detection with infrared thermography already exists and is helpful for measuring skin temperatures in large groups. However, the accuracy of these measurements does need to be evaluated. So we can see if we take this top left example here, we have some issues with this because the measurement you can see is taking in some of the background as well as the skin temperature. We've got body areas covered by clothing or other people, and we also don't know how the movement of these people is influencing the results. Although these automatic systems have been heavily developed recently for purposes such as COVID-19 detection in airports, they would also potentially provide a valuable tool for those interested in thermal comfort, especially if we wanted to look at, for example, people in offices or museums and galleries where we've got large groups of people moving through an open plan space, as this would allow us to make real-time measurements and then be able to alter our environment as well. The problem being, however, historical standardization of the method of infrared thermography has actually limited its use in the field. So we need to assess if we want to use it in this scenario, how moving subjects with limited exposed skin surface areas and in uncontrolled or changing environmental conditions may influence the measurements. So the aim of our study was to determine whether we could use infrared cameras to image and collect skin temperature measurements of people during movement, and whether this would vary by the camera type selected depending on the response, integration and capture times of the camera. We also wanted to look at how sensitive our mean skin temperatures are to any missing values, to the size of the region of interest that we place during the analysis, and also the sensitivity to any deviations in input parameters, which would include the skin emissivity, the reflected temperature, air temperature, relative humidity, and object distance. So how did we do this? Well, infrared and standard video were collected during the 2019 World Athletics Championships in Doha for the women's 20-kilometer race walk, and 18 athletes were analysed. A FLIR medium wave camera and long wave camera were placed on the U-turn of the track in order to allow us to take measurements of the anterior, lateral and posterior aspects of athletes. Both cameras were mounted and stabilised for a period of 45 minutes prior to the race, and a black and aluminium reference plate positioned to the side of the track for subsequent measurements of the reflected temperature and accuracy. Regions of interest were manually selected in FLIR Research IR software for laps 1, 5, 10, 15 and 20. And the mean environmental conditions over the duration of the race were 31.6 degrees Celsius air temperature, 76% relative humidity, 0.3 meters per second air velocity, and 29 degrees Celsius WBGT. So on to our findings. You can see here in the left image, we have quite heavy blurring of the legs versus in the right image where we see good clarity of all body areas. We found blurring to be primarily an issue on the leg, affecting, the images taken when moving laterally through the field of view, and more so for the long wave camera. Blurring is an issue because our measurements can become both a background and a skin temperature measurement. So just to explain that a bit further, in order to get a valid temperature measurement, the object you're trying to image must remain on the pixel of the sensor matrix for a sufficient amount of time. So in this scenario, the average athlete was moving at approximately 3.5 meters per second, or if we think of that as about 3 steps per second. This would equate for the long wave camera to a single leg moving 630 pixels per second. This means that in the exposure time of that camera, which was 30 milliseconds, the leg is moving over 19 pixels. And given that the average leg was about 12 pixels wide, this means that at one point in the exposure, 7 pixels are actually in fact a background measurement and not the leg for the whole exposure. When we compare this to the medium wave camera running at the same pace, a single leg moves 700 pixels per second, equating to 0.07 pixels in a single exposure time of 0.1 milliseconds. Thus, the athlete is static enough to achieve a sharp image and gather a measurement within the integration time. So as with the examples I showed earlier, in this scenario, we also had issues with missing sites because of factors such as clothing, obstructions from other athletes, cooling devices, that kind of thing. And so it was important that we assessed how these missing sites influenced our mean skin temperature calculation. So to do this, regions of interest were removed individually and in combinations from the calculated mean skin temperature and compared with that where we had all the body sites. And we found that the only meaningful impact came from the thighs, as removing these created a difference of 0.5 degrees Celsius. As we may have expected, when we remove sites in combinations, this had a greater impact on the mean skin temperature than each constituent part alone. Overall, this just supports the need for infrared thermography, but also all other skin temperature measurements to cover the largest body surface area possible in order to achieve a representative whole body measurement. Leading on from that, this led us to also look at how the size of the region of interest would influence the results. So we compared the temperature reading of a whole area covering that body site with 200 pixels of it and a single centrally placed pixel, as well as a central line and 100 pixels, and also the hottest and coldest pixel from this full area. And we found that as the surface area of the region of interest was reduced, a small positive bias became greater, and all of these alternative measurements were significantly different from this full area.
Sorry for interruption. Polly, you have less than 4 minutes.
Okay.
Time. Thank you.
Interestingly, taking the hottest or coldest pixel from the area introduced large differences of up to 1.3, of a mean of 1.3 degrees Celsius, again indicating that any reduction in the surface area will reduce the representativeness of the whole body. And this can vary quite significantly depending on the regional variation as well, and where we place that region of interest. Additionally, the variation between anterior, lateral and posterior measurements was investigated, and we found that anterior and lateral and anterior and posterior measurements were significantly different from each other. And so when we kind of combine that all together and compare that with some protocols that aim to standardize how people place regions of interest, we do need to consider that any reduction in the surface area is a loss of temperature data points. And so this highlights that we want the greatest number of pixels within our measurements and also the highest resolution of the camera possible. So finally, for accurate analysis, the following parameters are required by the post-processing software or the camera itself, including object emissivity, object distance, reflected temperature, air temperature, and relative humidity. Unfortunately, when we use these methods in the field, it's not possible to control these factors as accurately as we can in the laboratory, and we may have errors from not being able to make continuous measurements, or in this case, we couldn't place the measurements exactly where athletes were at all times. And so we looked at how sensitive the measurement was to deviations in these parameters. So looking at emissivity here on the table, typically emissivity of the skin is set to 0.5 to 0.98. However, for the medium wave camera that we used, which measures in the 3 to 5 micrometer wavelength band, it's actually should be set more at 0.91 to 0.92. And we should also take into consideration any impact of sweat with that emissivity. But we found that a change in emissivity from 0.98, which is what's commonly used, to 0.91 will alter the skin temperature measured by 0.07 degrees Celsius per 1 degree Celsius difference in reflected and object temperatures. And we found that for both cameras, the greater the difference between the reflected and object, or skin temperature in this case, the greater the sensitivity to emissivity. And conversely, the sensitivity to reflected temperature was dependent on the emissivity, increasing as emissivity lowered. We had the same relationship with air and object temperature, which was the same linear pattern. However, it was just a lower sensitivity to that than the reflected temperature. And sensitivity to relative humidity and distance were both small and dependent on air, but not reflected temperatures, with a less than 0.1 degrees Celsius deviation introduced by a plus or minus 5% change in relative humidity or 4 meter change in distance. So I'm okay to go on?
Yeah, your time is already finished, but if you want to tell something in a
Yeah.
second, less than second, I will be grateful because you are at conclusion and time. And thank you for your scheduling. Yeah, time scheduling. Yeah,
So I can just
finished.
quickly go.
Yeah, it's better.
Sorry. So
Thank,
yeah, just to.
thank you.
Okay.
Okay, thank you, Polly. Thank you, Polly. And also, one of the audience have a question from you. You can read it in the chat box, and at the end of our presentation, you can give the answer to this question. Okay, the next presentation is about, thank you, Polly. Thank you for your nice presentation.
Thank you.
The next presenter, you can stop your sharing. We can go directly to the third presentation about robust assessment method of future climate uncertainties. I guess you can start. The presenter, yeah.
Yeah, hi, just a quick check.
Yeah.
Can you see the presentation, not the slides?
Yeah.
Okay, perfect.
Yeah, go to next slide, please. Go to next slide.
Yeah, it works?
It works, it works,
Perfect.
yeah, thank
Perfect.
you. Thank you.
All
thank
right,
you.
so I'm gonna start. Hi everyone, I'm Prateek, and I'm a PhD candidate in the Building Physics and Services Research Group within the Faculty of Architecture and Built Environment at TU Delft. And today I'm going to be presenting my work I did as a part of my master thesis graduation project. So let's begin. So robustness as a concept is about the ability to withstand or overcome adverse condition, or basically it's about designing, keeping the future in mind. Now we design our buildings in terms of structurally, we keep it robust so that it stands for next 30 to 50 years or probably even more. But what about comfort? We should also include the robustness of the comfort within our design process, and especially when we are on the verge of climate change. So now in order to do that in the context of Netherlands as compared to other European countries. The Netherlands wants to reduce carbon emissions in order to reduce their impact with the climate change. And for that, they want to have the new construction or renovation focusing on energy reduction. And a large part of this energy reduction focuses on reducing the space heating consumption. Now, the design aspects, primary design strategies to reduce heating demands focuses on highly insulated building envelope, increasing your airtightness or increasing your glazing surfaces to maximize solar gain. But in summers, what happened is that these highly insulated envelope actually acts as a greenhouse effect, and it causes the risk of overheating. Now, overheating is one of the primary cause of thermal discomfort. And as we know that the global temperature is quite rising, it will eventually become a very difficult problem in future. And why we need to start looking into this, because we as occupants spend 90% of the time indoors, while for students, it's even more. From various studies, there has been found a correlation between thermal comfort and their productivity. And it's quite possible that the thermal comfort problem will only increase in educational buildings with further climate change. But then how do you reduce overheating? Well, we know of active measures and passive measures, which actually use different technologies or design to balance the heat balance of the building. However, climate change has a dynamic nature. Therefore, the strategies should be adaptive to this dynamic nature, but also it should be energy efficient. Therefore, passive strategies provide opportunities to interact and adapt to these external climate. But the main question here is that can passive strategies still help us reduce the problem of overheating or achieve thermal comfort in future? Therefore, the primary design aspect or primary research focus of my study was to assess with the robustness or future proofness of passive design strategies to mitigate risk of overheating in future climate scenarios, and specifically 2050 and 2085. The boundary conditions which I took for this research is that I'm only looking at outdoor temperature change as an indicator of climate change. And I'm focusing on energy efficient school buildings. And in terms of design strategies, my focus is primarily towards building envelope because it can accentuate the risk of overheating. So I've looked into passive strategies applicable at building envelope in the temperate climate because of the context of Netherlands. Now, to begin with, I selected few case studies so that I can apply my the methodology developed to analyze robustness. So I look into two different type of buildings, probably towards the extreme. One is the Pulse building in the Tudor campus, which is a highly energy efficient building, probably nearly zero energy building as well. It's mechanically controlled. And then the other one is a Melanchthon school. It's a secondary school in Rotterdam, again in Netherlands. And it's a naturally ventilated school. Now, if you really see these two schools, the Pulse building has quite high insulation based on passive design or passive house standards, while the Melanchthon school has also high insulation, but not as high as Pulse building. So these two case studies gave a good idea about what passive strategies can really do in these two extremes of educational buildings. So the next step was to identify spaces with overheating risk. So I looked at some literature. I did extensive literature review, and then I found that generally it is found that overheating happens in teaching spaces, of course, because of high internal loads. Within the orientation, south, southeast, northeast, and northwest has highest possibilities of overheating. And generally, spaces on the top floor has the highest probability of overheating because of heat gain via solar heat gain via sun, via facades and roof both. So first I looked into these spaces. I identified these spaces in both the case studies, and then I identified 7 spaces in Pulse building and 3 spaces in the school building, which may have a possibility of overheating. Now, to reduce the computational time to dynamically analyze these buildings, we started looking at an analytical method, which is temperature overrun in the month of July, which is suggested by the Dutch standards. And it is a static heat balance method, which tells you whether your space has a risk of overheating or not. So we applied this method on these 10 spaces. And after the application, we found 2 spaces in each of the case studies, which has the highest potential to overheat. Now, after that, we simulated these specific spaces in each buildings via dynamic simulation, Energy Plus and Design Builder. For assessing the risk of overheating, we looked at the Dutch Adaptive Thermal Comfort Model, which is also based on the EN 15251. It basically plots the operative temperature against the outdoor running mean temperature from past 7 days. If you see the graph on your right, you will see a resemblance with the shape of thermal comfort, which was already presented by Professor Fergus in his keynote lecture in the morning. So what it does is that there's a limit that, okay, only 10% of the occupied hours can be accepted as thermally discomfort. And according to ISO 74 for the educational buildings, it has to comply with Class B, which says that the percentage dissatisfied is only 10%. So what does it mean? If we really look at this chart, the percentage of discomfort hours, which I calculated via the simulation software, the 10% band is what is acceptable as comfortable, and anything up in the red band is the discomfort hours. So first I analyzed for the baseline 2008 test reference here, and we can see that all the identified spaces in both the case studies are more or less comfortable because they fall within the blue band. But in 2050, the percentage of discomfort hours due to summer overheating increases quite a lot. And in 2085, it becomes even worse. To understand this graph, what it means that if you are spending 100 hours, if you have occupied 100 hours in a space, in 2008, only 7 hours are discomfortable. In 2050, around 18 hours would be discomfort. And in 2085, around 30 hours would be uncomfortable due to summer overheating. So then the next aspect was, okay, what are the solutions we could apply in order to reduce this overheating? So to reduce overheating, the strategies applied on the building envelope can be divided, focusing on heat protection, control, and removal. So I made a map for integrating these passive design strategies on design level, which is pre-design stage, conceptual design stage, and system design stage. And these strategies are further divided as what is the objective of the strategy, where are you applying that strategy, and what is that strategy exactly. And then furthermore, I developed a map for the architects or designers to use, as in where to apply and when you can apply these kind of strategies. So this map on your rightmost part of the slide, you can see that heat protection has these kind of strategies available to be applied on building envelope. And similarly, heat control and heat removal, these kind of strategies can be applied on the building envelope. Now I looked at all these strategies applied on the dynamic simulation individually first to select, to see which application, which strategy has the highest impact in reducing overheating. And then finally, I combined certain strategies together, which has the highest impact, to see their individual impact. And these were some of these strategies, combination of these strategies, which I finally applied on both the case studies. Now, but how do you assess the robustness of these strategies? So a robust design is a design with minimum performance variability under the presence of uncertainties. But let's break this definition. So by design, I mean the solution sets, which are the applicable passive design strategies I showed you before. We apply it on using the building performance simulation, and we have to see the overheating hours as the performance indicator. And that is what we need to minimize in terms of performance variability under the presence of the uncertainties of climate change. So that is worst case scenario of 2050 and 2085. Once we have all the performances ready, we evaluate robustness using the statistical method of best case, worst case scenario, and then we report the results. So this best case, worst case scenario is basically the difference between the best performance of the entire design space and the worst performance of design across all the considered scenarios. And in this case, as I said, we need to reduce the minimum performance deviation. So the robust design would be the minimum performance between the worst case and the best case of all the designs together. So to see that, here is an example of one of the space in the Pulse building, which was on the top floor. Now we see that in 2050, as compared to the existing cases, these are the percentage of discomfort hours, and we can see that it makes the discomfort hours below close to 10 or below 10%, which was our limit.
Sorry for interruption. Yeah. You only have 1 minute to.
Okay. Okay.
Thank you.
All right. So I'm going to go quickly. So we applied this strategy on all the this method on all the spaces identified. And what we found that the robust design strategies identified from the method was quite helpful, because it could reduce around 54 to 43% of discomfort hours in future. But then that's not enough. We have to help architects or designers to also use robustness evaluation in the design process. So as an extension of my studies, I also developed a simple Excel tool, which is analytical based. So if you're really interested in looking into the tool, you can scan this QR code, and then it will take you to a live preview of the tool. And then finally, I would like to conclude that we shape our buildings, thereafter they shape us. It's a infamous quote by Winston Churchill, but what I say is that we shape the climate, therefore the climate will shape us now. And thank you for your attention, and looking forward for your questions.
Thank you so much for your time scheduling. Also your presentation was great. It's great, at least to me. I checked your app yesterday night using your quick QR code. I really like it, because some students and I work on app designer with MATLAB. I don't know you develop your app designer with MATLAB or not, but I really like your presentations. No, okay, we don't have time. Thank you for your presentation. We can go to the last presentation, and after that we have 15 minutes for question. Peter, if you kindly share your slides.
Yes. Yes, thank you, Mr. Chairman. I will try to share my screen.
Excellent.
Here it is, and I will move to presentation mode. Is that now seeable, my first slide for the audience?
Yeah.
That's working fine. So, good afternoon. It's my pleasure to present on behalf of my colleague Yorgos Koulis and myself the design and the nowadays operational details and the future of our pavilion at the Expo 2020 in Dubai. Dubai, you know, not more than 500 kilometers northwest of Oman, is now hosting the world's Expo. It's called 2020 because of Corona issues. It was delayed, and now it started in October the 1st. Austria is one of 192 countries that have a pavilion there. So to show the country, and it's financed by the Chamber of Economics. So they want to show what they can do as a country, not at least in economic affairs. This is the pavilion, the Austrian. It looks very different, but it's not about looking different. It's about making a difference. So we had the honor as climate engineers and building physicists, together with a general designer, that's the architectural office of Querkraft. We, together with a bundle of special engineers and consultants, we won an exhibition within Austria. There was an architectural exhibition who should build this pavilion, and Querkraft won. They are very professional, very enthusiastic, and very crazy in the best meaning of the word architects. They really like to bring things down to the extremes in terms of simplicity, and I like this approach very much. So this is the pavilion, and these are the people who worked with it. You see, it's really a different look-alike, surrounded by technical boxes of other pavilions. It serves a gross floor area of 1,260 square meters, with the uses of exhibition and innovation lab, which is a special area in the exhibition. And excuse me, I set my clock to be on time. Now it runs. Cafe, a VIP lounge, and office and service areas. It will be in service for half a year, having started now 2 weeks ago, and it will be open 12 hours a day. The construction idea is like this. It's made of a number of 38 cones. Originally, they have been planned to be made of loam for the temporary aspect of the building that would have fit very good to make them and to release them to the soil again. But the loan was unpayable, and it was not possible to get the permissions for the international standards and codes for safety reasons, etc., etc. So the loam idea had to be left, and now they are of precast concrete with clay plaster inside. They can be dismantled and carried away and re-erected again, and I hope they will. There are 4 heights of the cones, which have been deliberately designed to the purposes and to the wind and to the stack effect of ventilation. And the climate design idea is that it's really more of the half of the building is purely free running mode, and the other half is mixed mode, hybrid mode, with a lot of passive means of climatization. The headline for the design was really this reduced to the max. We did a lot of headaches and calculations to really get things as simple as possible. This is the floor plan. You can see the exhibition area. It's free running mode, fully entering here, floating through the area, getting into the planted courtyard and getting out, or getting into the cafe. And there are the VIP and the office area and the service area for storage and facilities. Green, in green, this is the free running area. In blue, this is the hybrid controlled area. Hybrid controlled means that during the night it's always free running. During the day, we decide upon the outside climate and the inside climate comparison. If it's in the controlled mode, then the openings are closed at the top of those cones, the doors are closed, and means of comfort ventilation are introduced, so desk fans, ceiling fans and other things, and small fan coils will run. If the climate allows, the doors are open, the lids are opened, and it's free running mode. We applied principles which are very common in the Arabic traditional architecture, the vernacular architecture. Many of them have been presented already in this wonderful conference. Many of them we learned from fruitful discussions with the scientists who invented the adaptive comfort. So many thanks to Sue Rove and Fergus Nicol and Michael Humphreys. We learned a lot from you. The principles of domes enhancing stratification and buoyancy ventilation, the principle of wind towers enhancing the effect of natural ventilation by low or lee situations of the wind, and not at least the principle of having shaded courtyards with and without plants, with and without water. So these are our design principles we realized in the pavilion. We applied reflective outer surface to have the sun mostly reflected. The shape of the cones themselves form a very well shaded area. And I loved the lecture, the keynote, or the lecture from Professor Knebel when he said light and air and no sun as a principle for the Arabic region. We increased air movement due to either the cones, which have stratification ventilation and work as solar chimneys, and increase the air movement downstairs, and very open layout in the exhibition. And we increased the air movement by fans in the green courtyards and by, yes, I said open doors, which are with metal mesh covered, even open during the nights. We apply the principle of night flushing and thermal mass by these massive cones, and we add elements of adiabatic cooling in the courtyards. And having been said today already in some of the lectures, we use the principle of adaptive comfort, and we learned from Fergus Nicol today in the morning that the majority of adaptation is taking place in simply changing clothing, and I will come to that later. Some images of the inside. This is the open, the free running mode area of the exhibition, very much connected to the courtyard, sometimes shaded. The big openings are shaded. The small openings, which are 15 meters height, are not shaded. Another image is here you see the small dry mist ventilators. We learned something about them. I will come to that later. These are images from the hybrid mode, part-time control zones. There we have the same elements like we have in the open area, but additive to this, we have the element of manually operable doors towards the courtyards. You see one of those doors here. Now it's in the closed mode. We have mechanically operable lids at the cones. So when we go for mechanical cooling, we close the cones. We go for preconditioned supply air in the controlled mode. Here you see the inlets for the controlled air. The inlets have been designed deliberately to introduce an air movement and comfort ventilation effect. So we deliberately designed them to have 0.7 to 1 meter per second air movement there to enhance the comfort, and we have ceiling fans which work very well, and some other under-dimensioned fan coils, not under-dimensioned but very scarcely dimensioned, fused from the controlled zone and fused to the cones in the erection phase with those movable lids. a picture from the VIP area, and again a picture from these big doors in the open mode, so opening to the controlled zones in the hybrid situation of free running mode. The design looks easy, but it was heavily prepared by CFD calculations, by building energy modeling. Here you see the wind distribution passing through the ground floor of the exhibition area. You see a lot of statistics we did to convince our clients, and convincing the clients was a very important thing. You can imagine telling them that they will be happy with 30 degrees and 32 degrees sometimes is a brutal start in the beginning. And all honor to our clients, they really listened, they really learned with us, and now I think they're most of the cases very happy with the pavilion. We had a brutal start. The pavilion was designed to start in mid of October, which in Dubai, you can see at the edge here, the outdoor climate starts to get very well suited for night ventilation. But due to Corona aspects, they started half a month earlier, which is a significant difference statistically in Dubai, with the night temperatures not falling below 25. And in fact, October 21 was 2 weeks where the outdoor temperatures did not significantly fall lower than 30 degrees. So you can imagine this pavilion had a tough start. But after the first 2 weeks, these are graphs from just 1 week ago. We are very proud that the indoor temperature in red is significantly lower than the outdoor temperature in gray. So the principle really works. That is the free running mode area with 5 and 7 degrees less inside than outside. So we're very happy that the prognosis and the design issues really proved. We have been very happy with the CBE thermal comfort tool. Many of you might know it. It's a very handy means of visualization of comfort, of prediction of comfort zones, including wind, including many aspects of adaptive measures. And it helped us a lot to visualize and to justify what we do. And it helped us in discussing comfort issues with our clients. What we learned that what really give us headaches in the first 2 weeks of operation is not and was not the building itself, but the technical equipment. We thought we have very little technical equipment, but still I could not imagine how many things can go wrong with simple stuff that I thought is normal. So this has to be fixed. It will be fixed, and it gives us headaches. There was a learning curve with our clients and with the people who work in the pavilion as regards dress code. We Austrians love to be nicely and fully dressed with shirt and jacket and long trousers and sneakers. They learned, the colleagues, that they sweat like hell when they dress like this in a climate of free running mode, adaptive comfort. So they changed dress code, and that was important. And we learned that for Europeans, acclimatization takes place within 2 weeks. So in the beginning, they said, this is horror. After 1 week, it was nice. We learned that the dry mist fans could have been slightly less noisy. And we learned that the mesh width of the permanent open doors could have been wider. You see here the mesh. It has a calculated opening factor of 70%, but still you can really see and measure that the driving wind is a little bit blocked, and it could have been wider, the mesh. We learned that under the extreme situations of the first 2 months of this October, we simply bought 10 ventilators and placed them in the neuralgic points, and they helped a lot. So again, air movement is the answer to neuralgic points. And we will leave them there for the next 2 weeks, and then we don't need them anymore because the climate is coming to winter situation. We're very happy that the building energy modeling and the CFD proved to be really right. So if you ask the right answers and do the right inputs. These are really things that work. After the Expo in a half year, there are good plans. There are negotiations with Professor
Sorry, Peter, for interruption. I guess your time is finished, but if you want, we can talk, for example.
Thank you very much. Thank you, Mr. Chairman. I am finished. We have the good offer from German Tech University in Oman that we might bring them our pavilion and replace them or re-erect them on their campus. We would be very happy and honored to do this. And just 2 days ago, even the Expo managers asked us if the pavilion couldn't stay there because it's so nice and so special. So we're very proud to say that the pavilion really makes they really look at it, and people come and look, and it works. And I do hope it's an example that makes a difference. Thank you very much.
Thank you, Peter. Thank you for your excellent presentations. I'm not in your field, but about the CFD, computational fluid dynamics, and also the utilizing, you need to be sure about that your CFD works well or not based on the data that you already maybe measured based on some sensor inside the buildings that you created. But it's excellent work, and congratulations, by the way. So we have 15 minutes time. Also, my colleague, Dr. Elena, can continue to lead this section instead of me. Dr. Elena, you can now also, I already write the questions, but I guess each of the audience can ask their question. We can start from Nahal. I guess one of the audience have a question from Nahal. You can start, yeah. Each of you, I guess, yeah.
Yes, thank you for the question. I didn't have much to present. So MPET is a reliable index for outdoor. It is to be compared with UTCI, which we used in the bigger part of the study, and to the outset. So these three indices actually were considered. MPET, the reason for that is that we are conducting a thorough investigation about each and every city through the tool MBMET, and that tool uses PET. So there is a direct correlation between MPET, which is the modified index, and PET. So this was the reason for the selection of that particular index. And the other side of the other part of the question, yes, in terms of blue urban infrastructures, of course, it is being considered in new cities, especially in new urban areas and developments. But it is to be considered with the aspect of heat rise and as well as consideration of water scarcity and water threats in terms of climate change. So the balance between both, I think, is very, very critical in terms of urban expansions.
Excellent, thank you. Thank you, Nahal, for your answer.
Yeah. Thank you.
Okay, the next question, I guess, from Polly. 2 questions already asked from Polly.
Yeah, thank you for your question. So the first one was about linking the objective measures of infrared with standard subjective thermal comfort measures. Yeah, I definitely agree with this point here. We understand that thermal comfort is an integration of many factors, not just the skin temperature, and in the lab we would definitely suggest using multiple measurements. But we just kind of wanted to give this skin temperature measurement as a possibility for where we have a scenario where we can't go up to everybody in a space and ask them about their thermal comfort. We can't take subjective measurements. And so skin temperature provides a way that we don't rely on any input from those people, and we could still be able to monitor their thermal comfort and change the conditions. Although, yeah, probably more work would be needed on establishing exactly the relationship between the skin temperature and the thermal comforts. And then the second question was about whether we can...
Covered, yeah.
take any of the clothing areas and look at the skin temperature there. Obviously we acknowledge that one of the limitations really of the infrared measurement is that we can't take a measurement under clothed areas like we would be able to with a contact method, unless we can use an infrared transparent clothing, but that's not really feasible in most scenarios. And it's tricky. We assume that skin temperature under the clothing is going to be warmer than the exposed skin, but unfortunately that is a kind of a limitation we have to accept with the method. So hopefully that answers them.
Thank you. Okay. If during the answering anyone of the presenters have any question, please write it in the chat box. Thank you, Polly. We can also I and another of the audience have questions about Patrick. You can start. Yeah.
Thank you for your questions. I'm not able to start my video because the host has blocked it, so I'm not sure. But anyway,
definitely I didn't block you. Maybe the host think that you forgot to turn off your video. Yeah.
Okay, maybe, now it works.
No, it works.
Okay. So the first question was, I think, from you. If you're asking if conditional value at risk is a better measure, or for robust design, if utilizing NINP is a good way. Yes, the answer is it could be. So I'm coming from a design background. So for me, the very immediate avenue to look how robustness is being tested was design background, design field. So which was very close to me was product design. So I started with looking at how does product owners or product designers look at robustness, something like Taguchi method and things like that. So I went from that perspective. I mean, I'm sure there are like numerous evaluation methods which could
be. Thank you. The point is that it's the only suggestions. Normally, because you mainly focus on uncertainties, and for uncertainties, one of the best methods for measuring risks, exactly when we want to quantify risk in a more appropriate way, especially those related to the humans, we can use the extreme risk that's called conditional value at risk. It's very easy, and you only do the frequency analysis based on the different value of your objectives of design, because the uncertainty resulted in different value for each objective, and as a result you can measure the risk. About the NINP, is really easy to apply. This concept is complicated, but it's really easy to apply. Briefly, it means you should have to minimize the fluctuation of your objective, design objectives. When you face uncertainties, you cannot control, for example, the temperature of the environment. This is the limitation of our design. So if you include these two methods and combine these together, it would be definitely progress in the edge of this knowledge for designing buildings. You can definitely go through this idea that I have, and you will see, you will face the music finally. You can understand that you can do something good in building design. It's only suggestion, no need to, it's not a question. It's not a question, honestly, but I worked previously on risk assessments and also the different optimization procedures. Taguchi and different response surface methods is really easy to apply for optimization. They are belong to optimization. These two methods, non-linear number programming, can be used in both simulation and optimization. In simulation, you can measure, which one of the objectives can change because of the uncertainties and reduce the fluctuation. It means robustness. The different interpretation of the concept of the robustness belong to minimizing the fluctuations. And great. About the second question, also other audience have a question from you.
I think it's about application of green strategies. If I looked into it.
Green strategies.
I did look into it, but I didn't apply while I was simulating it, because Yeah, I mean, there were practical reasons for not applying it. First of all, I mean, yeah, time constraints, because yeah, it was a very limited study I had to do. Also, if I remember correctly, it has to do with the complexity of the simulation model I had at that time and the software. But I think somewhere, as a future approach, I did say that it would be worthwhile to see the application of, to see if really green walls and roof in the context of Netherlands could really help reduce the overheating further. So yeah, that would be my answer for the question.
Thank you.
Yes, thank you so much.
Thank you so much. Thank you. I guess there are two questions from Peter, if I'm not mistaken.
Yeah, there's some. I go through them quickly. The change from earthen material to precast concrete dedicated by safety standards, that was the question about stability. Will the system last sandstorms of high speed? Will the system last? Can you guarantee that it will be of no danger to people? Can you guarantee? Always this question of static engineers or authorities, can you guarantee? No, with a system like loam that you design on site, you cannot guarantee. You can be sure, but you cannot guarantee. So it was a question of this official wording of giving guarantees. Next question: why did we select 28 degrees as a cutoff for changing from the free running mode to the controlled mode? That was an agreement with the client. The client was an owner of a cafe, and he said, "Hey, I am serving cakes there with sugar and chocolate, and I do not want to see my chocolate running down the knees of my clients." So it was an agreement from the viewpoint of operation of a cafe, and so it's closing down at 28. And it's opening again in the night. We have night ventilation always in the night, and during the day we keep it open until 28 is reached. Maybe we shift at that point, but it was an agreement with the operators of the cafe. The data acquisition for the data loggers inside the room on the full running mode area, we have the testo stuff with the Wi-Fi submission that works very well. We have it on our screens at home in Vienna. And for the central air handling unit and the fan coils, we have a Siemens system which supports us with the data, and we have the control screen in Austria too. Did the CFD simulation consider the earthen material? Yes, it did. So we always combine the CFD simulation, which we do with Phoenix, together with the building energy modeling, which we do with the British TAS from EDSL. So always do it in parallel and check the effect of the mass. How do the pavilion reflect Austria? Well, I hope it reflects Austria in this way, that we are that we can show that we are clever engineers and clever architects, but we do not think that we will save the world with technology. So we are good technicians, but we do not want to serve the world with technology, save it, but do contributions that are sensitive and a contribution respecting the place where we are. And we do not want to export technology. We want to serve thinking and cooperating. Could be in the best case. This is Austria. I hope it is. Yes, the answer is yes. I think free running mode systems can be justified very good and optimized very good and sensitively designed very good by dynamic simulation, but dynamic design systems. When environmental heat sources and heat sinks get in, again, very good designable with dynamic things. There's a clear yes. Dynamic design should be the basis, and it opens doors for less technology and less technical equipment.
Yeah. Thank you, Peter. Thank you for your nice answering the questions. Dr. Elena, can you hear me?
Yeah, I'm here. Yeah.
If you want to say something at the end of this section, I will be grateful. Also, after you, I can tell something about, and I'm really grateful to be here. And I heard and checked for presentation. All of them were nice. Now we can lead the section, Doctor.
Thank you, Dr. Mohammed, for doing all job for me. And thank you all presenters for being with us today and giving such very interesting presentations, sharing with us your ideas and research items. Thank you very much.
Thank you, Dr. Elena. Thank you. I'm also grateful that today I at least became more familiar with these topics. Thank you to everyone to attend in today's meeting about climate change and building design. The aim of this meeting is to have a shared vision about new approaches that can be used, and we talk about and cover at least to analyze and look at these methods, new things carefully. All of the 4 papers was excellent, and thank you audience for asking a lot of questions at the end of the presentation. The presenters, the audience can also, might suggest to keep going to collaborate with each other in near future. And at least all of the concept can be used in real world. And in my opinion, they are all good. Thank you all. I wish you all the best and nothing else.
Thank you very much. Bye.
Thank you. Bye.
Bye-bye.
Bye.